Good afternoon, my name is Peter Baumli. I'm extremely happy that I can show you my knowledge and my research. Today I will speak about nanomaterials and nanotechnology. As Kalevanan said, I'm from Hungary. Hungary is in the middle of Europe. As you can see, the capital of Hungary is Budapest, but I'm from the north part of Hungary. Its name is Miskolc. You see this very nice building from Budapest, from Miskolc. This is a castle, very nice area and snow. My students from India, they are very shocked when they arrived and they meet the snow. This is the main building of my university, and I would like to introduce my colleagues. I'm working as a leader of a research group, and my group contains at this moment 6 researchers, 2 of them from Hungary and 4 of them from other countries. First of all, I would like to speak about nanotechnology in general. What does it mean, nanotechnology? When we are speaking about nanotechnology, we are speaking about a range from between 1 and 100 nanometers range, where we try to do chemistry, engineering, modification, and manipulating to reach new materials. Here I connected 2 sentences that nanoscience is the study of the phenomena of the manipulation of materials, and technology is the design. In my research group, my topic is the design. I'm preparing the materials, nanostructures, and from this I would like to show you some slides. First of all, I would like to show you some pictures from the internet. You can find it. When we compare the normal hair with nanowire, you see this big wire is a normal human hair, and if we check the nanofibers, for example, carbon nanofibers, typically 500 times smaller, thinner than a hair. So this is very difficult to prepare, and in this case we have to say that the surface of the specific surface of the materials is extremely high. In our daily life we meet small entities, small materials, animals. I collected here some pictures. You see the end is 5 millimeter, the free 1 millimeter. Is extremely small, but we can go deeper, smaller area if we use scanning electron microscope, and we can see the eyes of flea as in the left hand side picture, or we can check the cell of blood, the red blood cell, which is 8 micrometer. And this is too big for the nanotechnology. The nanotechnology is in the range of, for example, viruses, as we can see on the left hand side, and the DNA in the right hand side picture, which its diameter is 2 nanometer. So I collected here a scale to imagine the nanomaterials, which is prepared by the man. You can see here below of this picture, right hand side, some atoms. We are able to move the material atom by atom on the surface of a substrate, and we can form some new drawings. Okay, so we have to categorize the nanomaterials according to the dimensions. And in this case, we can collect 4 groups of these nanomaterials. If you check the literature, you can find at least 2 different way of the groups. One of them, as you can see here, when we are speaking about the 0-dimension materials, and we are saying this is nano dots. The 3-dimensional is the nanoparticle. When we are speaking about that in the 3-dimension, all of the dimensions are below the 100 nanometer. Okay. Other group, when we are speaking that the 0-dimensional nanomaterial is, for example, nanoparticle, as you can see in this figure, and 3-dimensional material is, for example, a microporous composite electrode. As until now we saw, we can find different nanomaterials. For example, as you can see here, particles, which is for me the 0-dimensional materials, and you can see that these particles has different shapes. For example, below you can see that we can prepare flower-like structures, and these are also particles. According to the material, we can say that we can prepare metallic nanoparticles, for example, pure silver, gold, or compound nanoparticles, for example, oxide nanoparticles. The most important is zinc oxide or any other compounds, for example, ceramic nanoparticles or polymer nanoparticles. And we can decorate the surface of these nanoparticles, as you can see in this figure. When the material, the nanoparticle is prepared, the surface is decorated because we would like to modify the behavior of this nanostructure. Or we can group the shape of these particles. You can see this list. For example, a core shell structure we can prepare. In this case, we prepare a core nanoparticle and we cover its surface with another material. Or very interesting structure is so-called yolk shell. You can imagine this as an egg, and the particle is the outer part of the egg. Inner part is the yolk, and there is no white in this egg. This is the yolk shell structure. We can speak about the decorated structures, as we can see here in this figure, in this scheme, that we prepared this orange nanoparticle. Its surface is covered with a core, and the core is decorated, for example, with organic materials. You know, nanotechnology is not a new one, because in the 4th century, we can find a very nice cup, as you can see here in this picture. In this glass cup, you can find a lot of silver and gold nanoparticles, and because of this, the color of this cup could be modified. So this is an old technology. Nanofibers and tubes we can prepare also, as you can see here in this figure, and the materials of these tubes are metal, carbon, oxide, ceramics, and polymer, as in the particle situation. In this figure, I show silicon carbide fibers. We can also prepare coatings, for example, functional coatings. Here in the right-hand side, you can see so-called water repellent coating, and left-hand side, a brazing coating. I will speak about a little bit later. How can we synthesize the nanomaterials? We have two main groups of the preparation methods. One of them is top-down, and the other one is bottom-up. The top-down technique means that we have a big bulk material, and somehow with high energy, for example, with milling, we prepare smaller and smaller particles, and in this case, the surface area will be increased of the particles. The bottom-up technique means that we prepare the nanostructure atom by atom, and we build up the clusters and finally the nanostructure in this way. According to the used material, the phases we can group. As you can see here, we can prepare nanomaterials from gas, from solid, and from liquid materials. If we prepare from gas, we have to evaporate somehow the material of the nanostructure. From solid, we have to destroy the structure, and from liquid, we have to use chemical reactions. From gas phase, we can find a lot of techniques. The first is physical vapor deposition, PVD, where we use a target and we evaporate, for example, with plasma, the target, and on the surface of a substrate, we can form a very hard coating. This is good for cutting tools. Other important technique is the CVD and CVC method. In this case, we have to use chemical reaction during the evaporation of the material. Sorry, how can I go back? In this case, we use a target which has a chemical condition, but this is different than the desired nanostructure, nanocoating, or nanoparticle in this case. We can use so-called vapor liquid solid technique. It means that we use a vapor precursor material which contains the material of the nanostructure. We use a liquid phase which is a catalysator, and the product is solid. As you can see here in right-hand side, these wires we prepared with by VLS techniques. And very interesting for me, very interesting technique is its name is ALD, atomic layer deposition, when we are able to prepare a coating with atomic thick or molecular thick thickness. So we can build up the coating in this way. We say that one atomic layer thick coating we would like to prepare, and we are able to prepare one atomic layer thick coating using ALD. If we use liquid phase to prepare nanostructures, we have to use chemistry and chemical reactions. In this case, we have to prepare a solution from the material. For example, if we would like to prepare silver nanoparticle, in this case we have to use silver nitrate as a precursor. In this liquid silver nitrate, the silver ion is oxidized form, And because of this, we have to use reduction agent or electrochemistry. And in this way, we can prepare the desired silver nanoparticle. The problem is in this situation that we aren't able to control the size of the particles, and our product will be polydispersed. It means that polydispersed, that we can find, for example, 100 nanometer nanoparticle and 1 nanometer its diameter particle. So very big range we can find the particles. We can solve this problem if we use so-called microemulsion technique. In this case, we can control the size of the particles. Also is interesting technique, the non-aqueous soldier technique. In this case, non-aqueous means that until now we use, for example, water as a solvent. In this technique, because the material, the product could be sensitive and we would like to avoid water, in this case we use, for example, alcohol. And we can prepare a lot of materials. You can see here in this scheme that we can prepare aerogel, dense ceramic coatings, wet gel, xerogel, a lot of materials. And I have to mention finally the electrochemistry. This is also a very nice technique, and in this way we can control the thickness of the coating if we would like to prepare coatings. Here I show you some nanostructures. Here you are iron oxide with different shape. Platinum we can prepare, or using reduction or electrolysis technique we can prepare coating, as you can see here as a coating. Nanomaterials, we can prepare nanomaterials from solid phases, as I mentioned. In this case, we have to destroy the structure. This is the milling. And then using powder metallurgy, we can form, for example, composites or any other required products from this material. And the big question, why we would like to prepare these nanomaterials, what is the reason behind of this high energy work? And here you are a list why we prepare these materials, because we can modify the physical, the mechanical, chemical, and physicochemical behavior of this material if we compare with the bulk material. In the physical properties, you can see that optical, electrical, and thermal behavior we can modify. From the physical-chemical behavior, the adsorption and thermodynamical behavior can be modified. Okay. So I wanted to show you a figure that as we decrease the size of the material, and we can get smaller and smaller particles, the number of the atoms on the surface will be increased, and in the bulk will be decreased. And because of this, we can observe a very interesting situation, that the melting point of the material will be decreased. This is the melting point depression. I mean that if you use, for example, copper, the melting point of the copper is higher than 1000 degrees centigrade. And if we prepare nanostructure, for example, nano coatings from copper, we can reach the melting point of this nanostructured copper, for example, 500, 600 degrees centigrade or so. The optical properties of this material, you can see here these two pictures. This is cadmium selenide quantum dots. The material is same in all of these flasks, but the size of the nanoparticles are different, and because of this you can see different color of it. Or electrical properties, you know, we can speak about band gap, a separation between the conducting band and the valence band in the materials, and if this band gap is too high, the material will be not conductive in this case, and we can modify this band gap preparing nanostructure. And I would like to speak about applications. As you know, nanotechnology spans many areas. For example, medicine and health. You can see here, this is a fiction, science fiction could be. This is a drawing, but perhaps in the future, I don't know, in 10 years, we will be able to prepare small nano-sized robots which can operate something in the blood. Or now we prepare nanostructures for food and agricultural industry, you know, the packaging of the products. We can use in a security and defense industry also, biotechnology, when we would like to modify the DNA. Mechanical engineering, robotics, you can see this very small robot which can work. Informatic industry and technology. For example, textile, we can prepare new and new textile. We can prepare textile with new and new behaviors. And the most important thing is the energy, because we prepare a lot of energy and we have to save it, store it, and nanotechnology can help us in this field also. The first would be what I mentioned in the application is the so-called self-cleaning surface. You know, it's come from the nature, the lotus, the flower. Its leaf surface is decorated with very small wire, and because of this, the lotus able to clean itself. And now I would like to show you this video. If I'm sorry, Viraj, please. I go into this video because I wouldn't like to show everything. Here is a paper test. You see, this paper is covered with a special nano coating, and you can see the water repellency of this paper. If you check other paper which is not covered, you can see its surface will be wetted as a normal paper. You can see that the surface, which is covered with nano materials, nano coatings, is not wetted by water, and the water run away from the surface. But we can use, for example, timer. We can coat the timer, and we can place it in water, and we can check how it is working. And you see a normal timer will be dyed, and which is covered with nano material is working. Also tissue test. you see that as a normal situation, tissue is wetted, and the coated tissue doesn't wetted. Also deep in water. And oh well, I would like to show you this mustard. You aren't able to cover the bread with mustard if it is coated with this special material, or it is a sponge. It's wetted and doesn't. I'm waiting for the mud test. Yeah, this is the most funniest. You can study how can you prepare mud in this way, and how can you use it, and how can you save your clothes against. How can I stop it? Okay. The next application is the melting point depression. As I mentioned you that if we are able to prepare nanostructured materials, I mean that the copper, for example, in this case, the copper, the brazier filler material, we can prepare, for example, 5 nanometer thick or 10 nanometer thick coatings, and we can separate these copper layers from each other with a barrier layer, and we heat it up. We can observe that the melting point of this nanostructured copper will be between 500 and 900 degrees centigrade. It depends on the thickness of the layer. And you can see here in the right hand side picture that the copper came out from this multi-layered structure. And how can I start this video? I would like to show you, this is a video also from the YouTube. Here you can see a nice nanostructured brazier foil, and you can see with, what is this? Lighter, you can braze it, and here the guy place this nanostructured brazier into these two metal, and with a very small electricity, he's able to braze the metals to each other in yeah, this is better here. And the metal is brazed to each other very strongly. The next application is the energy storage, and I have to show you this story. This is the supercapacitor. In this case, we prepared nanosheets from agricultural waste, and we tried to use it as a capacitor, and we can later we can prepare an electrode from this material, and you can see that the charge discharge current is different. We can store electricity on this nanostructured material, which is supercapacitor, and we can use as a battery. The next application is nanocomposite coating. In this case, we prepared nano coating from aqueous solutions with reducing agent. And why this is nanostructured? Because as this coating was formed, this is a nickel phosphorus coating, This is the matrix material. The structure of it is nano-sized, and we used nano-sized titanium carbide particles as well. And this composite coating, good for mechanical properties, improve the mechanical properties, or improve the sensitivity of the substrate against acid or any other chemical materials. And the mechanical properties, for example, micro hardness, will be increased if we use nano particles as additive and as a reinforcement. You can see from this figure that a normal conventional nickel phosphorus coating hardness is around 600 HE. If we use conventional titanium dioxide reinforced nickel phosphorus coating, the hardness will be increased, but very high or higher hardness we can reach if we add titanium dioxide nanoparticles to this nickel phosphorus coating. And finally, I would like to say thank you, and I'm grateful to Dr. Kalayan and Tirupati for this webinar. And I have to say thank you to my students, as you can see here their name, and my colleagues also who investigate my samples. And we are working in a project in which we try to prepare the mentioned nanostructured brazier composite nano multi-layered system. And thank you for your kind attention and questions. Oh, yeah.
Thank you, Peter. Thank you, Peter, for your presentation. You really nailed it. I mean, it was really good and clear. And there are a few questions which some of our students asked. One of our students is, how does it able to repel the liquid? I mean, he asked the question when you show the tissue paper and the paper, right? So how does it able to repel the liquid? This was the question asked by one of our students.
Yes, you know, so I have spray, hydrophobic spray, and we sprayed the surface of it. This is how can I say? So this is this coating is prepared by non-aerosol gel technology. In this case, silicon dioxide, amorphous silicon dioxide coating is formed on the surface of this tissue, for example, and the end of this amorphous silicon dioxide coating is decorated with, for example, CH3 groups, and these are hydrophobic part, and because of this, the tissue is water repellent.
And thank you for the question answering. And there's one more question which one of the professor would like to ask. How the adherence of the nano coating with the substrate is tested? Did you get the question right? How the adherence of the nano coatings with the substrate is tested?
Oh, well, yeah, we can investigate it by peeling test, or there is a special rotating test where we use a ball and we move on the surface of it, circular, and we can check the edge of this crater which is formed.
Fine. And there's one more question, Peter. Thank you for answering that. What is micro hardness? It was asked by one of our students. What is micro hardness? What is micro hardness? Yeah, and how it's measured?
Oh, this is a special machine. You know hardness? This is the question that the hardness test, you know? So I mean, a small diamond pyramid is placed in a special machine, and we use very small weight, and we press this diamond into the material, and then we measure the print, what is remained in the material, and from this we can identify the micro hardness. So it is the same as the normal hardness test, just in this case we use this smaller smaller pyramid and smaller weight.
Okay, fine. So, and there's one more question from one of the faculties. Titanium dioxide is used as a coating in dress with the photocatalytic properties.
Yeah.
I mean, it can be used or not. That's what our question is, I guess.
So titanium dioxide has photoactive and photocatalytic behavior, and it is good for example, a window or in the car, you know, so the windshield, sorry, just windshield.
It's all right.
You can use, because the surface will be cleaned itself. So, you know, this I showed this self-cleaning behavior. We have to group in two main opportunities. One of them, what I showed, that the surface won't wetted by water, and the surface is water repellent. This is the lotus effect. The other one, when the surface is perfectly wetted, I didn't show it, the surface is perfectly wetted. In this case, we use titanium dioxide as a coating on this, for example, a window, and the water perfectly wetted the surface, and this photoactive photocatalytic reaction can clean the window, and the perfectly wetted water can move and clean the surface after this chemical reaction.
Thank you, Peter. And there is one more question. That was the nanomaterial can be characterized both nanomaterials can be characterized as coatings. Nano coatings can be characterized as both chem, SEM, and AFM. So which one do you think is best?
You know, we use TEM, transmission electron microscopy. Scanning also could be good. We use now this focused ion beam scanning electron microscopy, and in this case, in situ, during the measuring by scanning, we can prepare the cross section of the sample, and it could be also good. You know, the resolution is
that's the most.
Say to you which technique is good for you, because scanning is not able to see just the atom or the clusters sometimes. So the TEM would be good, or any other techniques.
Could be fine. And
TEM is the most important, I think.
TEM, right? So, and there's one more question from our student. So, is it nanofibers are used in clothes? I mean, is there materials clothes are made up of using nanofibers, and what are the, and is there any medicinal application in this nanotechnology is used in medicine or not?
Yes, so textile industry is used also, and perhaps in healthcare industry could be good.
Fine, thank you. And
so the fibers is interesting, you know. So this is very thin material, so you can just decorate the surface of it, and you can modify the surface of the textile. So this is the application, or you know, as a holder, any other materials, you can decorate the surface of the nanotubes, for example, or nanofibers with any other active materials, for example, silver nanoparticles. And for example, it could be good against viruses and bacteria, because this could be antibacterial behavior.
And thank you, Peter, for answering the question. There's one last question. And what is the cost of making this nanomaterials? I mean, it's really super duper expensive, or like, well, it's good. Generally, what would be the cost?
You know, it is a good question, because in your daily life, you are able to prepare nanostructures, nanomaterials. If you drawing with graphite, you know, very small powder of the graphite will be formed on the paper around the drawing. This is nanostructure also. Or you know, I spoke about graphene, and also if you use glue tape and you place on the surface of graphite, this glue tape, and you remove this glue tape from the graphite, in this case you can prepare graphene.
Yeah.
You know, and this American and Russian scientists who did the same at home, more or less at home, you know, that they use this glue tape, and you know, they fix the glue tape on the surface of graphite, remove it, and then another glue tape was fixed to the first one, and they do it, and finally they place this glue tape into the transition electron microscope, and they discovered the graphene, one atomic layer thick graphite, and they got the Nobel Prize because of this. So this is very easy, very, very cheap, because you have to buy just a piece of graphite, and you have to buy
and the tape, and then just do it, right.
And just this. So this is cheap. But if you would like to prepare, for example, this 5 nanometer thick multi-layered coating, in this case you have to buy a PVD machine, which is extremely expensive cost. So, you know, it's two different places.
Yes. And there is some more questions, Peter. Does nanomaterials used in quantum computing? It was asked by one of our students. In quantum computing, does nanomaterials can be used?
May I say, I don't know?
It's okay, you're allowed to say. And there is one more. What is the durability of this nanomaterial? I mean, how long they can withstand? For example, if I'm going to buy some expensive nanomaterial, what is the durability? How long they can, do you understand, right? The durability of the nanomaterials.
Their life.
I never measured it.
Okay.
So, what can I say? So it depends on the application and the nanomaterials, because if I'm checking a so-called colloidal system means that there is a big amount of water, and you disperse very fine solid particles in this water. This is a colloidal system. Its name is Sol. If something happened, pH will be changed, the composition of the air around this. In this case, this Sol will be decomposed, and the particles will be moved to the bottom of the container, you know, so it will be dyed. So how long during the life of this material is depend on the application and depend
the
on
usage.
the
Yeah.
material. How can you disperse? So it's not an easy question. It's specified to a given material.
Fine. There's one more question. And does a nanomaterial affect the environment? Like nowadays, we are going for eco-friendly, isn't it? So how does this nanomaterial impact on environmental? Because, you know, my project is also for eco-friendly, right? I changed it to...
how can I say? So if we are speaking about nanotechnology, as in my presentation, I showed that the nanotechnology is good. I showed the best side of the nanotechnology, but we have to speak about the bad side of nanotechnology. Perhaps if I can get other opportunity for same webinar, I can show you the bad side of the nanotechnology.
Sure, Peter.
How can I say? these fine particles can cause very big problems, not just in environment, in the skin of the ladies. You know, the ladies cover the skin with different creams. These creams contains very small particles, and perhaps these small particles move into the skin. But other in environmental, we can find the good side of or best side of these nanostructures, because as I showed you, this iron oxide nanoparticles we can use for cleaning the soil. If there is oil contamination, we can use, or any other heavy metal contamination in the soil, we can use these nanoparticles to clean the surface, clean the soil. So we
yeah,
can find best and worst side of this.
Okay, but and there is one more question from one of the professor, like what nanomaterial is dangerous or micromaterials dangerous? I mean, which is more dangerous? That's what he asked. It seems. So, which is the most dangerous one? What is your opinion?
What can I say? Smaller could be more dangerous.
More dangerous, isn't to clean up and the environment and stuff like that.
You know, because the micro-sized particles you are able to filter. You know, in this situation, if you use a mask, you can filter the powder from the dust from the air. But the viruses, because this is smaller, you aren't able to filter, and they can go through this mask. And
that's so
true. A smaller particle can be problematic.
There's one more really interesting question of one, I don't know, one of a student asked, isn't if nanomaterial is this much useful, why don't they make this raincoat as nanomaterial? That till now we don't receive any nanomaterial raincoats, and why is it not raincoats?
To repel the rain.
I guess you.
Why don't repel?
Yeah.
Because this is expensive.
Fine. So I guess you answered in the short. This is expensive.
It would be nice, but you know, this is how can I say? This is an industrial question. Until we buy the raincoat from plastic, nobody will prepare a nanomaterial coated
raincoat,
because this is good enough.
But it's super duper expensive. Yeah, fine. So I guess, do you mind answering one more question, or it's done? Fine. Okay. Thank you, Peter, for attending.
So my brain is filled up.
Fine. Okay. So I'll wrap it up. So thank you for giving this webinar, and it's really helpful for our student as well. And in a short period of time, I called you here for attending for giving a webinar series. It's really good. And
I see here another question. Sorry.
Yeah, like
if nanotech can increase surface area, can solar panels be made? Yes, it is used. So nanotechnology is used for solar. Sometimes is used for solar energy. The nanodots are used. I mentioned the nanodots, and they are used in solar panel preparation.